Okay, hi, my name is Geir Eide. I am with the Tessent Embedded Analytics team at Siemens EDA. And over the next 20 minutes or so, I'm going to talk about Tessent Embedded Analytics and how to use functional monitors to help accelerate SoC debug and provide valuable data throughout the life cycle of a semiconductor. And what's driving a lot of this has to do with complexity. And I'm sure you've heard a lot of talk about system complexity. I have my own personal definition of system complexity, and might not be the industry standard, but I think of something being as too complex is if either I, as an individual, as an end user, have to reboot the system on a regular basis, or if I, as an end user, have to update the firmware on the system on a regular basis. And like many of people, I first got introduced to this whole concept of having to reboot the system back in the 80s and starting using PCs and Control-Alt-Delete. And the engineer who actually implemented or invented Control-Alt-Delete, was an IBM engineer. He once attended, I was in a conversation with lots of other people celebrating the anniversary of the IBM PC, and he said, I might have invented Control-Alt-Delete, but it was Bill Gates who made it popular. And, that whole, this really illustrates what complexity is about. It's not just about bigger designs, bigger ICs, smaller transistors. It's about the interaction between hardware and software and an environment that it's in. Now, since then, a lot of things have happened, and again, I've learned to live with having to reboot my phone, my tablet, the hatch of my door, and also update the firmware on my washing machine. But really what's driving this system complexity is the fact that we have workloads being defined by different market segments. We have systems running in a wide range of environments, either in a cloud, in a data center, on the edge, and again, systems consisting of complex components all put together. And it's the combination of all of these things, of the segment, of the workload, of the environment, of the components of the chip itself that's driving this overall complexity. So to be able to deal with this, to address this, what we need is the ability to monitor, measure performance, get visibility of what's happening inside the design. And we need this to help us both in the early debug phases as well as through deployment and use of the design. And we need this visibility to be able to provide feedback both to software developers and also to impact the next generation of the design itself. So validation has always been an important part of design implementation. That goes without saying. But where things have been changing over the last several years is that it's not just as much about the IC anymore. It's about the entire system. And it's about being able to validate real system workloads, again, not just in the validation and development phases, but as we deploy the devices itself. And that's when we see that many of the traditional tools by themselves is starting to run out of steam. They're not designed to be able to provide the automated validation and characterization that we need to validate modern SoCs. And what we need also is be able to get feedback not just of how bits travel through the IC, but get the behavioral data, be able to continuously improve on the design, provide feedback that can be leveraged when you update the systems through its lifetime. Now, so Tessent Embedded Analytics is a system consisting of kind of two key components, what we call functional monitors or functional instruments, which is delivered as RTL IP, and together with dedicated software, embedded software, and also host software that allows you to observe what's happening in the design when it's running real software in the actual system. And this is, again, allows us to answer, deal with various different situations and answer questions such as, why doesn't the software operate the way it's supposed to be? Why is it running slow? Why do I have things that don't quite operate the way I expect them to? And why does my system work well in the lab and behave differently once it's in the system? So the intent of this instrumentation and this system is to be able to help me answer and address these questions. So as I mentioned, the key components here is a series of instruments, and when you look at the kind of a generic representation of a modern SoC with different types of processors, different types of accelerators, memories, and so forth, these functional instruments, each of them have the ability to basically add to monitor behavior associated with the different components of the design. So starting out with a trace encoder, for instance, which provides a mechanism to monitor the program execution of a CPU in real time. And it captures the instructions, the data, memory accesses, and outputs this data in a compressed format. Again, giving you the right blend of compression and visibility into the design. A more generic instrument, if you will, is what we call a bus monitor that allows you to observe non-intrusively transactions on the bus from initiators to targets. And like the other instruments, these are runtime configurable, which means that at runtime, you can configure these monitors to decide which information you want to see. For instance, you might be only interested in transactions coming from one initiator to a particular target, or transactions associated with a particular region of the memory. And you can get data like duration of a transaction, latency, and so forth. Other instrumentation includes the status monitor, which is like an embedded logic analyzer. And we also have devices or instruments like the processor analytic module, or PAM, which provides run control and performance monitoring for different types of embedded processors. And also, to give you another example, the static instrumentation, which is a non-intrusive mechanism for code instrumentation. Now, so this is a kind of an example of some of the different monitors that can be integrated into your design. And what ties all of this together is, well, what's shown in these little teal-colored wires here, which is really the messaging, and what we call the messaging infrastructure, so the dedicated infrastructure that allows you to configure and capture data from all of these instruments in real time. So again, this is a dedicated network, a dedicated infrastructure that does not impact the functional operation of the chip, does not require you to only access the monitors in an offline or a test mode. Now, from this network, you can then get data out of the chip, or also access the instruments through embedded software through what we call the communicators. So there are external communicators that allows you to, for instance, through USB 2 or USB 3, control instruments externally, or also send data out of the design. And also internal communicators that allows you to access the instrumentation from embedded software. So I'm going to take a quick look at a couple of use cases to give an idea of the type of data that you can get from the system, whether it's being used during debug or other phases of the life cycle. So one example is, for instance, when you are using the bus monitor to look for a deadlock or a hang system or hang conditions in a system, where a transaction starts but never completes, or doesn't complete in a certain time frame. And the way we can use the bus monitor in this case is to configure it at runtime to look for transactions completing within a certain time frame, and if that time frame is exceeded, the bus monitor will have captured within the internal buffer the sequence of transactions leading up to it. And that will allow the bus monitor to then alert either the system or a kind of dedicated CPU the content of the internal buffers and everything kind of leading up to this condition. Another use case is in context of characterizing code behavior, such as characterizing the cache line placement, replacement, and the impact it has on the system behavior in terms of latency on the system. And again, this is something that we can do with the bus monitor. We can capture the data, offload it off chip, and then process it, analyze it, and for instance, correlate it with other data sources like voltage and timing. Another use case I want to cover has to do with analyzing memory bandwidth. So in a system with multiple CPUs, each CPU might be responsible for different parts of the system, and we have optimized like each task separately, and we see that when all of these CPUs run together, that something starts to hang or misbehave or does no longer run in an optimized fashion. And the root cause of that could be that while like one task is accessing the memory with a high bandwidth, another task is trying to do the same. And again, by being able to have that additional the visibility where we can see exactly where these requests come from and why the memory bandwidth is being consumed. Without that visibility, it's very hard to debug and understand where this comes from. And it's that additional visibility that is being provided with the embedded analytics. And we have talked about this also in context of being able to get this visibility from outside. It's also important to point out that running and getting access to these instruments can also be done internally to the chip itself. So to do that, we can have one CPU basically communicate with the instrument and be able to get to kind of capture the data on chip rather than controlling everything from the outside. So we've talked about how these functional instruments and Tessent Embedded Analytics can be used in different cases. For instance, for the chip developer, for the system integrator, for the software developers, this type of design visibility allows you to debug software and get the product out the door faster. And deliver a product with fewer bugs, and also help you optimize the software. In the next phase, if you will, of the product's lifetime, once the system is in, or the chip SoC is in a system and is in a kind of a functional environment, this type of instrumentation also allows you to then continue to optimize the applications under real workloads and continue to use the same instrumentation to collect data, not just in a lab environment, but under real operating conditions. And this is something, again, as the design goes into the real environment, whether it is a chip that goes into a server, into a data center, or in other environments, allow you to continue to provide that visibility into what's happening inside the designs. So, again, Tessent Embedded Analytics is a portfolio of IP or embedded monitors, instrumentations that gives you additional visibility into the design that's helpful for the debug as well as the deployment phase of the product. And what allows you to really get the full power of this instrumentation is also a set of software utilities and tools that allows you to accelerate debug, but also connect this instrument to your embedded applications. For those of you who are interested in learning more about this, one resource you will find online that was published recently is from one of our users that presented at the recent user-to-user conference that we had, the Siemens EDA user-to-user. This is from Seagate that explained how they used the Tessent Embedded Analytics instrumentation as part of their process transitioning from an internal CPU architecture and started adopting RISC-V. So I hope this has given you a little bit insight into Tessent Embedded Analytics, which, by the way, is part of what we call the Tessent Silicon Lifecycle Solutions, or the Tessent product family. In the Tessent product family, it extends from design, where we help insert testability and observability into the designs, through production, where we help reducing manufacturing test cost and monitor and improve yield, and then towards the topics we talked about today, towards debug and deployment, where we provide additional utilities to help you accelerate SoC debug and validation and collect data through the life cycle of the design. So with that, I would like to thank you very much for your time. If you're interested in learning more about Tessent and Tessent Embedded Analytics, I invite you to look at the other resources that we have available online. Thank you.